In week 6 of Modern Geometry at Bellevue University, we're going to look at medial and orthic triangles. Our first proof has to do with a medial triangle. Recall that a medial triangle occurs when we connect the three medians of our triangle. Our proof is to show that the four triangles created by the medial triangle are congruent. So we are given triangle ABC, which is our original triangle, and we're going to let each sideline be bisected by midpoints DEF on AB, AC, and AB respectively. So of course, that gives us that AE is congruent to EC, that CD is congruent to DB, and that FB is congruent to FA. Again, by the midpoint theorem, or definition of a midpoint. We are trying to prove that the four triangles are congruent. So AFE is congruent to FBD, is congruent to EDC, is congruent to DEF. Now we know that the only ways to show triangles are congruent are to show side, angle, side, angle, side, angle, side, 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 or angle, angle, side. In this case, we have a lot of sides so far, but we don't have any angles, so it seems like side, side, side might be the best way to go. But again, how do I bridge the gap? I've got some segments that are congruent, but that interior triangle, the medial triangle itself of EDF, doesn't have any congruencies. So what I can do is I can use Euclid's proposition VI2 that says if you have a triangle with segments on it that are divided in the same ratio, so obviously this is a ratio if I'm looking at triangle AFE compared to triangle ABC, as we've done many times before, this is a triangle in a ratio of 1 to 2. So based on that, I'm going to get rid of some of these markings so it doesn't get too crazy. So based on that, we can say that FE is parallel to BC. We can say that ED is parallel to AB, and we can say that FD is parallel to AC. Now, why would this make a difference? Because now I have some parallelograms. So for instance, if I look at FBDE, FBDE is considered a parallelogram because opposite sides are parallel. And by Euclid's proposition I34, I know that opposite sides of a parallelogram are congruent. So that means BD, which I have marked with 2 lines previously, is congruent to FE. And that FB, which I had recently or previously marked with 3 lines, is congruent to ED. Now, in the same way that I did that, I can also say that AFDE is a parallelogram. And if AFDE is a parallelogram, just as I did before, where I had certain markings, AF had 3 markings and ED already has 3 markings, but the one remaining is that AE had 1 marking and that FD now has 1 marking. So if I get rid of all of the other hubbub, which can make it a little bit confusing, if I only keep those green markings that show which segments are congruent, it becomes pretty clear to me that each of those triangles has one sideline marked with 1 line, one sideline marked with 2 lines, and one sideline marked with 3 lines, and therefore they are congruent. So how would I write this up? I basically walked through the proof with you, but here's how I would write this up. By Euclid's proposition, we know that those segments are parallel. Therefore, we've got a parallelogram and opposite sides congruent. And then we have another parallelogram with opposite sides congruent. And then using those congruencies and the midpoint congruences, which you can certainly write out, you can say AE is congruent to EC, CD is congruent to DB, and BF is congruent to FA, all by the midpoint theorem. We can show that the triangles are congruent by side, side, side. For our next proof, we're going to take a look at a proof involving an orthic triangle. And an orthic triangle is created using the altitudes of the sidelines of the triangle. And so I did want to go through this construction with you because if you don't extend the sidelines of the triangle, your construction isn't going to work. So notice I have triangle ABC, but I'm going to go ahead and create a segment across from A, a segment across from B, I'm sorry, not a segment, a line. So I'm essentially taking those segments and extending them. Now, if I go to perpendicular line from A to the opposite sideline, and B to the opposite sideline, and C to the opposite sideline, and then I go ahead and construct those points. This is point A prime, and this is point B prime, and this is point C prime. So now if I just go to my hide tool and I get rid of those extra sidelines, and I can even get rid of the altitudes because really all I care about is those points created. So I just want to make sure those points created are still on my triangle. So here I have triangle ABC, and now I can go ahead and create this orthic triangle as well. Whoops, maybe. Let's try again. Go to polygon and A prime, B prime, C prime, back to A prime. So that is the orthic triangle along with my original triangle ABC. Now the theorem that I'm going to prove has to do with the kind of triangle needed to have B prime be on the interior of the triangle. So again, I would do some playing around to determine, but the theorem I'm asked to prove is to show that B prime is going to lie on the interior of AC, so AC being right here. So B prime is going to be between A and C only if BAC and ACB are acute. So this angle A and this angle C. So I can see by doing some experimenting, obviously A is not acute and B prime is not in the interior of AC. So you get the idea that this is what I would do before I would do a proof so that I could come and then make that determination. But again, if I wouldn't have made those sidelines of AC and AB and BC longer, then as I continued to do this, those A prime and B prime or C prime points would all just disappear. So that's just a little hint for you as you're going through your GeoGebra work this week. So I don't want to complete this proof for you because I only gave you 2 proofs this week, but I do want to give you an idea of how you would go about the proof. Start with a given of let triangle ABC be a triangle and A prime, B prime, C prime be an orthic triangle with A prime, B prime, C prime as the feet of the altitudes. And we're trying to prove that basically B prime is between A and C if and only if the measure of angle BAC is less than 90 and the measure of angle ACB is less than 90. So we're just going to consider cases. We're going to say case 1 is that B prime is actually equal to point A, or B prime is equal to point C. So as a hint, I want you to notice what must happen to that angle if those are the same point. For case 2, I want you to consider that either B prime is to the outside of AC on one side, or that B prime is to the outside of AC on the other side. Okay, so again, I have one pictured here where it's B prime, then A, then C. And I want you to take a look at the resulting angle. And the last one I want you to look at is case 3, where obviously it goes in the order in which we're asked, A, B prime, C. And I want you to look at the resulting angles that are in question. So what you might want to look at when making this proof, and this is your last hint, is to use the exterior angle theorem for case 2 and case 3, and for case 1, think about the definition of an altitude.